Okay, so single replacement, reviewing real quick, we're taking an element in a compound, we're creating a new compound and a different element. The element is going to displace one of the elements in the compound, take its place. Okay? You can identify the single replacement reaction by looking at finding that it's an element plus a compound giving you an element plus a compound. Examples here, we see that K is going to switch with the hydrogen in the water. We already went over that last time, but we're going to reiterate and go over these again and how to predict them and write the correct formulas. Also here, another example, the zinc is replacing the copper or displacing the copper. You can call it replacement or displacement. You might see it written both ways. Now, the main thing that you need to figure out and be able to read is the activity series. The activity series will always be provided. You'll have the table. You just need to be able to read the table and interpret it correctly. We do kind of expect that you know this one all by yourself. So here, for the halogens, we kind of expect that you know this one just based off of your periodic trends. Remember, for nonmetals, the trend for increasing reactivity is over to the right and up the group, so up and over. Fluorine is the most reactive nonmetal on the table. We really look at the single replacements in terms of the halogens replacing each other. So fluorine can replace chlorine, bromine, and iodine. Anything underneath it is less reactive. Chlorine can replace bromine and iodine. Bromine can only replace iodine. Iodine, of course, doesn't have any reactive power to displace any of the other three. So this one we kind of expect you to just be able to look at your periodic table and know that fluorine is the most reactive. It just goes down the group and so forth. The activity series of metals, though, this one, you'll usually see hydrogen on there as well because hydrogen is in acids, which we use as a reactant a lot. So the hydrogen will switch places with the metals. So you'll see that one also on there, but it's usually a table of metals and their reactivities. Remembering that the ones near the top are the most reactive, the ones at the bottom are least reactive. And in order to take another element's place in the compound, must be more reactive. Has to have that reactivity power to force the other one out and take its place and form the bond. So we're looking at this, you always must verify first, is it more reactive? Is it going to kick out the other element out of the compound and displace it? So be aware though, on any test or quiz you'll be provided the activity series and the solubility rules, so you don't have to memorize any of those, you just have to read and interpret them. So we already did 1, 2, and 3, and we did 4, 5, and 6. No, we didn't do 4, 5, and 6? Okay, so let's look at 4, 5, and 6. Take a look here. The first thing I do with 4, though, is aluminum and water. I change water to what? HOH, yes, because we want to be able to replace the cation there. Now, after looking at here, what can replace what, I look at my activity series. Is aluminum higher than hydrogen on the activity series? Yes, it is. Good. Since it's higher, it's more reactive, it will take its place. So that means hydrogen is going to form the other element, and since hydrogen's diatomic, I have to write it as H2. Now for the other product, I have to look at the oxidation numbers and figure out how the ionic compound is going to form in what formula unit ratio. So what is aluminum's charge when it forms a compound? +3, good. How about hydroxide? -1, right? So it's going to be a 3-to-1 ratio. So we have AlOH3, like so. Then the last thing we would want to do here is balance, right? So we need a 3 here, right? No, that's not going to work. We have a 2, 3 going on. 2 3s mean what? We have a 2 here, and the 3 here. So we have to do a what? When we have that 2 3 arrangement for balancing, what do we do? Least common multiple, which is 6. So here, I'm going to put a 2 here. Here, I'm going to put a 3 here. And then here I need a 6. And then in front of the aluminums, I need a 2. Very good. 3-2 relationship, make sure you look for that least common multiple. It's the easiest strategy to go with. How about number 5? We have fluorine reacting with calcium chloride. Is the fluorine more reactive than the chlorine? Because the fluorine will replace the chlorine because they're both going to be anions if they're in a compound. So yes, fluorine is more reactive. So the chlorine will come over here and be one of your products. And remember, chlorine is also diatomic. Don't forget to put Cl2. Now, what is the charge of fluorine normally when it's in a compound? -1. What's calcium's charge? What? It is an alkaline earth metal group 2A. +2, very good, it's a +2. So when we reform our compound, it's going to be CaF2, right? Are we balanced? Yes, this one nicely balances on its own because both fluorine and chlorine are diatomic. How about the last one down there, looking at the copper and silver nitrate? This particular case, what are we getting here? Is copper more reactive than silver? Yes, on the activity series it is, right? Silver is near the bottom, right? So is copper, but I think copper is just a few steps above it. So in our compound here, we're going to end up getting silver as one of our products. The copper, though, in this particular case, what is nitrate's charge? -1. Now, copper is multiple oxidation metal and can do +1 or +2. I usually stick with the one that is the same charge as the anion, the same oxidation number, to do 1-to-1 there. So I would probably go with the +1 here for copper and make my other one CuNO3. Now, if you did write CuNO3 too, that would be fine too, because copper does go to +2 as well. But usually it's easier to just stick with the same oxidation state as the anion if you can. Both would be acceptable answers, although the second one you would have to balance. Okay? So, do we have to do anything here for balancing? No, right? Everything is 1-to-1 here. All right, so. Very good. Let's look at 7 through 10, sort of 11-ish. All right. How about number 7? Who's going to switch places if they switch places? Zinc with sodium. Now, is zinc more reactive than sodium? That would be a no. So guess what this one is?
No reaction.
This is NR, no reaction. Yes, very good. How about number 8? Potassium and magnesium. Those are the two that might switch. Magnesium and potassium. Is magnesium more reactive than potassium? No. Once again, that one's lower on the activity series. So this one is also
no reaction.
No reaction. Thank you. How about number 9? Is iron more reactive than which element? Hydrogen is what it would switch places with. Yes, so is iron more reactive than hydrogen? Yes, it is. So it is going to switch places. So we have this possibility here. What is, we get hydrogen, of course, is one of our products, which is H2. Phosphate, though, what is phosphate's charge? It is -3. So in this case, iron has 2 possible oxidation states, +2, +3. I would go with the +3 here, because it's just simply 1-to-1 ratio here, so FePO4, because you have the possibility of being +2 or +3 if you're iron. Like I said, it's just easier. You could still predict the products and make it, the other one would be, what, Fe3PO4 2. You can predict it to be that one instead. That would be iron 2 phosphate. However, like I said, it doesn't really matter. You would have also, hydrogen as your other one there. But in terms of balancing, the other one's easier to balance. So, and at this point, I would accept both answers. So here, once again, we have the 3, 2 going on. So what do we need to do? 3 and a 2, and what else? 2 for the iron 3 phosphate and 2 for the iron over there. Very good. And our last one down here, I know it says 11 on your paper, but I made it a 10 up here on the PowerPoint. Is chlorine more reactive than iodine? Yes, it is. So it's going to kick out the iodine, and we would get KCl plus I2. I know that because potassium's a +1 charge, and chlorine would go to -1 when it's in a compound. This is basic 1-to-1 here, very simple halogen swap. And balancing is very simple. What do we do here? 2 here for your KCl, 2 here for your Ki. So far, so good? All right. Now let's take a look at our new solubility rule chart that's easier to follow. I just want you, though, to realize what these abbreviations mean. It tells you right here, SOL means that more than 3 grams of the substance dissolves. Dissolves means soluble. SOL means soluble. Okay? PPT here, that indicates that it forms the precipitate, which means it's going to be a solid. The little S symbol goes next to the compound. Now, I want to point out to you, because the other chart is a tad bit harder to read. This one's easier to read because it kind of gives you rows and columns to follow. Anything that's an alkali metal, that's group 1 metal. Anything with ammonium, which would be +1 there, as you can see, are all soluble. So if you see lithium, sodium, potassium, rubidium, any of the alkali metals within the compound, it's automatically soluble. If you see ammonium in the compound, it's automatically soluble. Now, this is the interesting part here. You've got your silver, mercury, lead combos. They're usually exceptions. They usually form precipitates with things that you would typically think are soluble. So they are soluble with nitrate, acetate, chlorate, and perchlorate, but you start going down the rest of the group, everything else is going to be insoluble or a precipitate with silver, lead, or mercury. Barium and strontium have a few little exception rules too, so pay attention to them. Calcium has a few, magnesium a few, and then other metals, that would be like any other metal with a chromate is going to be a precipitate, so that counts aluminum in there, that would count like nickel, that would count any other metal. Same thing for hydroxides and sulfides, phosphates and carbonates. So phosphates, carbonates, hydroxides, and sulfides are typically insoluble. This one even has chromates on there for you as well. Okay, so use this chart to your advantage to predict the solubility rules. There's also descriptions at the bottom here. Those are easy to read and tell you what to do here. Like, for instance, all common salts with the alkali metals are always soluble. So is this ammonium, common acetates. Acetate, remember, this is just the way we write it in the organic form, but acetate is C2H3O2-. That's also a different way to write acetate. If you read these down here too, that will hopefully clarify anything that you're not getting from the chart. Yes, question? No question? All right, let's go back to working a few problems with this. All right, chemical change involving the exchange of positive ions between two compounds. You have the double swap. Precipitate, a gas or molecular compound such as water is usually formed. Precipitate formed, remember we designate it with the new phase symbol over here. You get the S in there to tell whether it's a precipitate or not. And then here showing a neutralization reaction where we get liquid. That's another one where we're showing different phase on here. Remember, solids, liquid, and gases are pure substances too. They would not break apart into ions. You would keep them together when you're doing complete and net ionic equations. Looking back at the aqueous solutions, anything with AQ means it's got ionic compounds that dissociate in water. That means they break apart into their ions. So anything with AQ, you'd break apart into their ions. So looking at a complete ionic equation shows the dissolved ions as dissociated and free. So we break them all up. The only one we keep together is the solid because it's a pure substance and it's chemically bonded together, holding it together and making it fall out of solution and drop to the bottom of the test tube or beaker. Now what you'll see here is there are ions on both sides of the arrow. There are ions on the reactant and ions on the product side that remain unchanged. Those ions on both sides that remain unchanged are called spectators. They are sitting in the water watching the show. They are not involved in the reaction. They are not breaking bonds or forming new bonds, so they don't participate at all. So the net ionic equation is what we care about. We want to know which ones are actually doing the reacting, which ones are forming new bonds, and that would be here looking at this, we would look at and cross out our spectators, nitrate, sodium, and what we would be left with is the actual ions that are reacting, the silver and the chloride, forming the new substance, silver chloride or precipitate. We're going to do a lot of practice with this in just a minute of writing out complete net ionic equations. So definitely going to do some practice here. Now, this is a solubility chart. Of course, like I said, I would use the other one that I just gave you and explained. It'd be easier to find the exceptions. We already went through this last time, so I'm going to go ahead and move on here. All right, we already did 1 and 2, right? And we did 3 and 4 as well, yes? So let's look at 5, 6, and 7. All right, remembering this is the easiest way to do double replacement. You kind of do it, I think they still call it this in math, I'm not sure. I do like the foil thing, where I do the outer and then the inner, like so. I figure out outer one goes to the outer one, the inners go together. Then I look for oxidation numbers, like sodium. What's sodium's charge? Plus. Plus 1, what's carbonate? -2. And calcium? +2. And chloride? -1. So I know how to recombine them on the other side with their correct ratio. So if sodium goes with chloride, it's going to just be 1 to 1 because it's +1 -1. So it'd be NaCl. Over here, the calcium is +2, the carbonate's -2. So that is also a 1 to 1 relationship. CaCO3. Now let's look for balancing. Who's going to balance who? What do we need to do?
2.
We need a 2 here. Anything else? Good. Now we go to our solubility rules. We look for phases. NaCl, is it soluble or is it going to be a solid and precipitate? AQ or S? AQ, very good. So we put an AQ next to this guy. How about calcium carbonate? Is that AQ or S? This one is insoluble. It forms a precipitate, so we would put the little S symbol by it. Looking at the next one, let's do the outers. Ammonium goes with nitrate. Magnesium is going to go with the phosphate. Now we look at oxidation numbers. Ammonium's charge is always +1. How about phosphate? Phosphate's -3. How about magnesium? +2 and nitrate -1. Okay, so now we can recombine them correctly. Ammonium nitrate is 1 to 1. And the magnesium phosphate, that's going to be Mg, gets a 3. PO4 is going to get a 2. Now looking balancing wise, what do we need to do? I'm going to put a 3 here to get my magnesiums in balance. What does that do to my nitrates? 6. So we put a 6 here. Ammonium's going to need what? 6. So what do we put in front of this one over here? A 2. Does that fix everything? Yes. Now looking at our solubility rules. Ammonium nitrate. Ammonium's always soluble. Nitrate's always soluble. So AQ or S? AQ. Very good. That one's easy. Magnesium phosphates. Phosphates are typically what? They're typically insoluble. Few exceptions, but mostly insoluble. So magnesium phosphate, AQ or S? S. Very good. Solid. Precipitate. Our last example here, we have sodium chloride and nitric acid. So let's go ahead and combine them. They're pretty easy. All right, and sodium's +1, chlorine's -1, H is +1, nitrate's -1. So this is all 1-to-1, very easy stuff. NaNO3 plus HCl. Do we need to do anything for balancing? No. Okay, now phases. NaNO3, AQ or S? AQ. Sodium, alkali metal, always soluble. Nitrate, always soluble, so this is AQ. How about HCl? Have you ever thought of an acid? What phase is an acid in? It is. It's dissolved in water. It produces hydrogen ions in water, so it has to be AQ. Very good. All right, any questions on this? Because we're going to start doing complete net ionic equations next. So that'll be the next part of the predicting products. All right.